Okay, so apparently we left off with the ability of a capacitor to store electricity is known as capacitance and is measured in farads for Michael Faraday. So a funny thing here is that this isn't working. That's the funny part. Here's the problem.
Have you tested continuity? Open circuit.
Well, I'm glad somebody knew it was an open circuit. Look at that. All right, so 1 farad, it's like point I under what we just did. 1 farad. 1 farad is a very large unit of measure. Quite large. 1 farad, 1F, can store 1 coulomb. Remember what a coulomb is? Come on. C-O-U-L. I don't remember how to spell it. O-M-B. 1 coulomb. Store 1 coulomb at 1 volt. 1 coulomb is, I remember it this way, it's pi times 2, so 6.28. 6.28 times 10 to the 18th power. That many. So that's a lot. Electrons. That many electrons. So therefore, capacitance is often represented as picofarads. Picofarads. The picofarad, V-I-C-O-F-A-R-A-D, which is 1 times 10 to the negative 12. This right here is a 0.025 farad capacitor. 0.025. That's a pretty large capacitor. This one off my air conditioner is 55 micro on one side and 5 microfarads on the other. That's 2 capacitors in one. Two in one. All right, capacitance depends upon 3 items. So 3 items. 1, or I, the area of the plates. Obviously, the bigger the plates, the more electrons you can have. So more plate area equals more capacitance. The thickness of the dielectric which is to say that the closer you bring the plates together, the more they're going to attract electrons onto the plates. If you spread it apart, not so much. So we want very thin dielectric. So the closer the plates, the more electrons are attracted, the more electrons are attracted to the opposite plate. And the third thing that the capacitance depends on is the dielectric material. Common material for dielectric air, glass, ceramic, plastics, paper, air is considered the standard. Air is the standard, which doesn't mean it's the one you always use. It's just what everything is based upon. So air is a standard with a dielectric constant of 1.
So is that to say that these plates are wrapped up in such a way that they don't touch each other?
Yes, they touch each other, they short out. So we could touch on that. So one of the problems with capacitors is that that's exactly what happens, is the dielectric material, in this case it's tissue paper, will break down. Or you can get, if you get enough voltage through here, it's going to arc through the paper. And when you create an arc spot, and if you weld two pieces of plates together, then you have a short at that particular spot, which then you start to lose your capacitance. So that's why you have to test them with certain testers at higher voltages. You can't just test it with an ohm meter and go, well, you know, it's certain, it doesn't work. You got to use an appropriate tester to see what's going on inside there. And they break down and just start to wear out and don't work forever. That is why I have this one here. This came off of my air conditioner at home. So you guys that live at home with mom and dad, don't worry about it. When you don't, shit sad. Who lives at home with mom and dad? Let me see that. Don't do it. Don't do it. Right? But when your air conditioner doesn't work, 9 times out of 10, it's this thing. When the start capacitor goes out, the motor won't start and the air conditioner won't go. So you got to start capacitor. And they're very cheap. Let's see. We need to write this. Dielectric strength, the ability of a dielectric to resist breakdown, known as leakage. Yeah, we probably should, because they do talk about leakage. Let's see, A, air is the medium. B, dielectric strength. Dielectric strength, ability of the dielectric to resist breakdown. To resist breakdown. Which is known as leakage. You don't want leakage. The working voltage of a capacitor This is a Q&A question?
It is.
I thought so. Like, why would I put this in here? Because it's a Q&A question. Working voltage of a capacitor is the highest voltage voltage that can steadily be applied to a capacitor without the dielectric breaking down. Is the highest voltage that can steadily be applied to a capacitor without the dielectric breaking down. It's technically the whole voltage is dependent upon the type and thickness of dielectric, so it is dependent on the type and thickness of the dielectric. And should be, so working voltage should be 150% higher than the highest voltage applied. So if we had a 120 volt AC system, VAC, volt AC system, what would be the working voltage? Well, that'd be 120 times 150% equals 180 volts working voltage.
AC, would that be peak or RMS?
RMS. I think it would work out either way if you just kept it constant. If you said it was peak and you figured it in peak, and then you had the capacitor rated peak, but I think it's rated RMS.
Okay. Because otherwise peak of 120 is like a 167 or something, and then 150% of that. Back much difference.
Okay. Yeah. Well, but here's the thing. If you have to select a capacitor to go back in an aircraft, which one do you put back in?
Same one you took out.
Pretty close. The exact one that's called for in the parts manual. So typically what I will do when you're replacing anything, you pull it out of the aircraft, you look at the part number, then you look up what it should be to make sure the two match. If the two don't match, then you stop and you go, what's going on? Why do I have one that's different than with the parts manual? Because I don't trust parts manuals all that much. In fact, building engines, that was a large part of my job, was just trying to keep up with part numbers. I had a whole library of stuff. You know, people come in, oh, I need this part out of this book. Well, that's not right because it was superseded to this, because you have that, if you have that, it's superseded to that, and then this is the one you want for that. And then, whoa, okay, that's not what the parts book says. Yeah, I know. So that's the way parts books are. I don't trust them. And I don't know why that changed to red. I didn't do it. Capacitors. Capacitor in DC circuits. So just like with inductors, we're going to talk about capacitors in DC circuits, and we'll take it over to AC circuits. So a capacitor in a DC circuit, capacitor in a DC circuit, in a DC series circuit, will act as an open because it is schematically correct. In a series circuit, if I just drew something like that, put a load in it because you always have one load, what's current flow? Zero, because you have a gigantic open right here. That is open right there, open. Nothing flows. Well, it'll charge up, but then it stops flowing. Lights. Here I have my capacitor, and it is in series with that light. It's a very large capacitor. And it's all charged up right now. And
Can you just barely nudge that little chair right there, just a little out of the way? Thank you.
well, there, it's on. Nothing's flowing. If I discharge it. Now it's discharging. So it's stored up electricity, and then I discharge it out. And I go back on, it's got nothing. But on, it's in series, so we'll have it flow. How long will it flow? 5 time constants. How did you know I was going to say that? Because that was
5.
Conductors.
No.
Close for 5. All right, and we discharge it, and that just takes it back the other way. How's that wired? So in series, that was all that's good for. So in series, it's an open. So if it's a really large capacitor like that, as it's charging up, what happens is electrons are going to flow, and they're going to fill up this plate, and that is going to repel the electrons that are on this plate through our light up until this is completely charged. And once that plate's charged, then this no longer forces electrons out because it's discharged on that plate. And there we go. Then we discharged it. We opened up a circuit going the other way, and it just did the opposite thing. So this plate is all charged up, and so we discharged it back around. It fills up this way, and then makes electrons go that way. So it's pretty much going to be an open as soon as that charges up. So that is completely pointless at that point and does you no good. Now in parallel, let's see, and I actually have that. I'm going to write that. Capacitor will charge up and current will stop flowing. So current stops flowing as soon as it charges. I'll write it. The capacitor will charge. Will charge up, and current will stop flowing. And that is that. Now in parallel, they actually have a really cool function. So the capacitor, if I could find a shortcut for capacitor, in parallel, will act as a reservoir. So that would be some sort of power source. Have our load. And then just put it here. One of the things that this is used for, let's draw this a little different, is that when you get to magnetos, magnetos have a breaker points, and that is run off of a cam, which is sort of engine driven, and this little thing goes around, the points open and close. And there's some other stuff going on that we'll get into when we get into magnetos. But this is no longer a battery. We'll say it's a very large AC source. And so we have a rather large source of electricity right here, and it's going to go off onto some coils, more or less. And what you end up getting is a pretty large current going through this, or I should say voltage. It's a very high voltage. And so when you have a high voltage can jump a gap. And so what would happen is every time you started to open these points, because there's so much voltage, as you're opening it, the voltage is going to jump across the gap, and it's going to burn and arc those points as they open up. But with the capacitor, what happens is as these points start to open, all of the electrons, which are flowing out of here, headed to the points, they see that the resistance starts to build up on those points. And as that resistance builds up, the electrons are going to realize that the capacitor is a much easier route to go. So they kind of turn around, if you will, don't really, and they start filling up this. Like, hey, everybody, I found a shortcut, because it's AC, in this case, but we could do the same thing with DC. It looks like a shortcut. And so it'll start filling up this plate. Well, by the time it fills up that plate, these points have opened up so much that the voltage no longer can jump that gap, and so it's safe. Or we could go back to a reservoir theory that I have here. We'll talk more about that later. a reservoir theory where we have something in. And if we had some sort of load that, or some reason why there was a sudden decrease in voltage, then this acts like a very small battery that can kind of take the load. It can also act as a filter. So when you get spikes, they'll tend to go into the capacitor, and when you get drops off, they'll also go into the capacitor. So act as a reservoir. So we'll say act as reservoir. It can be used to chop out, or can be used to smooth out choppy DC. It's not a very straight line. Maybe it's out of a generator or something where it's not exactly straight. That'll help straighten it out. Can be used to protect points in a magneto. And if it's big enough, it can supply current for a short time. How long? 5 times, yes. So if a capacitor is connected in series and voltage is applied, current would flow at maximum until the capacitor is charged, and then it dies off. At the point the capacitor is charged, no current flows, and the voltage of the capacitor opposes the battery. All right. I'm going to skip some of those things. Keep it simple. Time constants. Well, it's a capacitor, though. Time constants. All right, so just like an inductor, it takes time to charge a capacitor. So just like an inductor, it takes time to charge a capacitor. The formula is time equals resistance times capacitance. So time equals resistance times capacitance. What was the formula for inductors? What's that? Nope, that was inductive reactance.
63.2%.
That was the time constant.
Inductance over resistance.
For the inductor, for a coil, or inductor, I'll say inductor. If you remember, it's time equals inductance divided by resistance. There. Not that I'm going to hold you to that, but hey, there we are. Oh yeah, this is something I was going to suggest. That you should have another piece of paper just kind of sitting by the side there, and I would make that sheet my formulas sheet, where I would keep track of formulas, and I'll tell you which formulas to put on there. So how long does it take? So just like an inductor, it takes 5 time constants. And that's all I have to say about that, because we already know what time constant is and how it came up with it and everything else. Can I move this?
Yeah.
All right, let's talk about capacitance. In AC. All right, because AC is constantly changing, a capacitor will charge and discharge continuously, making it appear as though current flows through it when in fact this is not true. I can write all that. Because AC is constantly changing. What's it changing in?
Amplitude
Yep.
and
It periodically reverses.
and duration, yes.
The capacitor will charge and discharge constantly, making it appear as though current flows through it. When in fact this is not true. Sort of. If you put enough voltage in a small capacitor, it will flow through it. That doesn't count. But if you have an appropriately rated capacitor working within its appropriate working parameters, and you hook it up with an AC, put a light there, will the light shine?
Yes.
Yes, it will. Unless you had a frequency that was so low that it charged up, got your five time constants, it completely charged, and you were still not through with the cycle. Then it would be like me doing this, the cycle going very slowly, and then going, well, we're still not done with the cycle. It'd be like, well, it's dead. I thought you said it flowed through it. Well, it would if you go fast enough. There we go. All right. So that's assuming that it's appropriately rated and installed in the right way. Okay, when voltage is applied. All right, so in this case with the capacitor, it's going to be the opposite of what happened with an inductor. So remember, with an inductor, as the Eli voltage leads the current. That's the E comes before the I. The L is for an inductor. So what happens is Eli, the voltage spikes out, and then the current that starts going through it creates a counter current that pushes back on the current. So current takes a long time to get through the coil, but the voltage goes up like it's supposed to right away. So you remember this, and everybody's cool with that?
Yes.
Okay, if you're not, just kind of go like this. So I'll talk more about it. So, all right, but in a capacitor, as we start with a sine wave at the bottom, and we start to go up, voltage is going to go up. Let's see, start at the bottom. Let's screw this up. It's the ice part. So the current leads the voltage. I don't want to say it wrong and confuse you. So as we start out, as before with the inductor, voltage takes off, and then the current, the electrons, kind of follow along. Like I said, the parents at Six Flags. That's me. Watch my kids. I'm coming. All right, but in this case with the capacitor, the current takes off because the current sees absolutely nothing standing in its way. So there is zero resistance right here. So no resistance. I mean, it is just going off to the races. And so the electrons just flow into this just as fast as can be, faster than the voltage will actually keep up. So boom, they're gone, and the voltage is still building up. So what the heck just happened, man? The electrons are gone. Where'd the little guys go? Well, they filled up that plate. Here comes the voltage. So that's why we have the ice part, ICE. The C stands for capacitance, and we have the I before the E. So that means that the current leads the voltage. All right, so when voltage is applied, maximum current flows instantly. When voltage is applied, maximum current flows instantly. This is because the capacitor plate easily takes a charge, which is the flow of electrons. So this is because the capacitor plates easily take a charge, which is the flow of electrons. Flow of electrons. So max current happens as soon as voltage moves off of zero. Off of 0 volts. So in AC, max current is, I actually have my notes at 0 degrees. So I'll put just past 0 degrees. So as soon as it leaves 0, boom, max current. Is that going to be in phase or out of phase?
Out of phase.
Yeah, by quite a bit, like 90 degrees. If I drew that out, here's voltage. And here's current. Max current would be here. So the difference between here and where it should be is how many degrees? 90 degrees. So therefore, let me see. Well, as electrons build up on the plates, the capacitor, I'll write that. So as electrons build up on the plates, the capacitor opposes additional current flow. So there is 0 current flow when voltage is at max. There is 0 current flow at max voltage. So to finish my drawing then, here's max voltage. This should come down here to 0 and start its way the other way. Therefore, current leads voltage by 90 degrees. So then, looking at my little sketch here, as soon as the voltage starts its way down, then the capacitor starts decreasing. The capacitor discharges, keeping the current flowing. So it just starts, but flows the other way. As voltage passes through 180, the capacitor, which is fully discharged, allows current to flow and receives a charge. The amount of current the capacitor allows to flow is dependent on the capacitance, capacitor, and frequency. We should write that. The amount of current that a capacitor allows to flow is dependent on the capacitance of the capacitor, dependent on the capacitance and frequency. So larger capacitor will allow more electrons to flow, will allow, let's say, higher current. And higher frequency. Will allow higher current. Which should make sense. If the plates are bigger, it's going to allow more current to flow to fill the plates. If the frequency is really slow and it reverses once every hour, well, you're going to not get much because it's going to charge up within the first few seconds and then do nothing for the next 59 minutes and so many seconds. But if you have it reversing very fast and the capacitor never even fills up, well, you're going to get a lot of current flow. All right, total capacitance in a circuit. How do we compute that? So total capacitance in a circuit. It is the opposite of resistors. It is the opposite of resistors.
Which one? D, C?
I don't know, because it went to I here.
Okay.
Oh, I guess it's large I, or it's out here I.
Just like
Okay, opposite of resistors and inductors. So in parallel, parallel, it is the capacitance total equals capacitance of 1 plus capacitance of 2 plus capacitance of 3, on and on and on. And the reason why it's like that is because when you put them in parallel, you can see that I can add up all of the surface area of the capacitors. So electrons coming in are going to see that. They're going to go this way, they can come down this way, they can come down this way. And so all of these plates are added up. So if I said, you know, if each one of these was, just for the hell of it, you know, an inch apart, then how many inches total do I have? I have 3 inches. You see what I'm saying? All right. But in series, you know what I'm going to say, I hope, is capacitance total equals 1 over C1 plus 1 over C2 plus 1 over C3, on and on and on. And the reason why that is because if you think about it, if I apply a power to this in a series circuit and the electrons are flowing, well, they're going to fill up this and repel off of this plate to this way. And so that's going to be a diminished amount that will fill up this, which then causes these right here, which is a diminished amount, to go that way, which is a diminished amount here, which causes a diminished amount there. So you have this decreasing amount of plates and force so it doesn't add up. It's a lot less. Hopefully that made sense. How? And if you think about it, it's kind of weird. It's like the electrons in this box right here are the same. They'll get wore out. I mean, they don't really, but they're like the same electrons. They never move. They never go anywhere. They just go from one plate to the next in their whole lives, and they can't ever leave that little space because they're kind of blocked in there because there's actually a dielectric keeping them from going any further than that. So that's all they do. It's very sad for them. It's like little electrons in a little electron zoo. But all right, the reasoning is that when capacitors are in series, the total capacitance is less because the center two plates do not contribute to capacitance. In a parallel circuit, the total plate area is added together because each capacitor acts independently. Oh, that's a nice way of saying it. Total capacitance is the amount of capacitance, but that does not tell us the actual opposition to current flow. Ah, that's right. That doesn't tell us the opposition to current flow, does it? It just tells us what the capacitance is. So just like inductors, we can figure out the total inductance, but it doesn't tell us what the resistance is. So how do we figure out the resistance of inductors? We use that formula, X of L equals 2 pi FL, X of L. Well, guess what it is with capacitors? We had inductive reactance, now we're going to have capacitive reactance. Which is the opposition of current flow. Opposition to current flow. Oh, so why the hell would I say that? Because this page goes way back here. We weren't even ready to talk about that. Again, I don't know if this is, I don't like this word, but I'm going to use it because it works. And yes. Measured in ohms, but due to phase shift is not considered resistance. But due to phase shift is not considered resistance. It's like resistance, but it's not. Represented as X of C. So X of C, capacitive reactance, X of C, now I can just shortcut, is inversely proportional to the capacitance and frequency. To capacitance and frequency. In other words, capacitance, in other words, reactance, or X of C, will decrease if capacitance or frequency increase. So if you increase the size of the capacitor, you get less X of C. If you increase the frequency, you get less X of C. And I go back to the same thing, go to extremes. If you have a sine wave that is very, very slowly, your frequency is extremely slow, it's like kind of reversing once every few minutes. That is going to be a lot of capacitive reactance. But if it's going very quickly, then it acts like it flows through the capacitor much easier. Or if you have a larger capacitor, it looks like it flows through it a lot easier. So you lose the X of C. All right, let's see. Formula. formula. Formula is x of c equals 2 pi f c. Sound familiar? 1 over. Because it's the inverse. So the other one is 2 pi fl. This is 2 pi fc, but it's the inverse. So it's 1 over. So if you had a piece of paper and you were keeping track of the formulas that you should know, I would say that I would want to put on there definitely how do you add inductors, how would you add capacitors, series and parallel. I would want to have x of L equals 2 pi FL. I would want to have x of C equals 2 pi FC 1 over. Those are the things I would want to see.
Can you say that all over again?
It's recorded. You can just watch the recording.
That's gonna be posted.
He's like thinking about what kind of bad thing he wanted to say to me, I could tell. No, I wasn't going to say it. I was just thinking it. All right, you ready?
Yeah.
Where'd you leave off?
Add capacitors.
How to add inductors in series and parallel.
Yeah.
Then capacitors, series and parallel.
Yep.
Okay, you got that?
Yep.
Well, you're well, okay. Then I kind of put a little box on that because it's kind of setting off to the side. Then I would put x of L equals 2 pi FL. And then the x of C is 2 pi FC, but 1 over. And those were the things I would want on my paper at this point in time.
You want time constants?
Now. All right, what would be the capacitive reactance? What is x of C if we have a frequency of 60 hertz and a capacitance is 100 microfarads? And get used to that because farads are almost always going to come in a micro or a pico. What'd you get?
26.526 ohms.
Woohoo! I got 26.5258, so I can do 5.3 ohms. Everybody know how to get that? All right. Let's take a break and then have more fun after this. Now the fun begins.